Now, the next thing that I would like to talk about, so let us move on now to the next topic. Let us take, we looked at an op amp, let us see how we can put op amps to use. Of course, you are familiar with many common applications, right, inverting amplifier, non-inverting amplifier, blah blah blah. Now, let us take a look at another application which you are most likely not familiar with, okay. And the motivation for designing or attempting to design such blocks is the following. So, it turns out that in a lot of electronic systems, you need to measure a voltage, right, with absolute accuracy, right. So, and convert it into digital form, all right. So, in other words, for example, I do not know, maybe you are measuring, you have a multimeter and you want to measure voltage, right, or you want to measure weight of an object, and the weight of an object is usually measured by a sensor which is some kind of bridge, right, and these are two identical resistors, and this is connected to some voltage Vref, all right, and you are standing on the weigh scale, and it turns out that the way the sensor is built is that if you stand on the weigh scale, this resistance increases with weight and this resistor decreases with weight, okay. And so, if no weight is put, then these two are exactly identical. If you stand on the weigh scale, then one resistor goes up, one resistor goes down. So, the difference in voltage between those two leads basically represents the weight that you are putting on, and clearly that difference is dependent on the reference, right. And so, if you want an accurate picture of the weight, if you want an accurate measure of the weight, that reference better be absolutely accurate, right. You might think, well, how does it matter whether it shows me as weighing like 50 kilos or 60 kilos, right, it's maybe only a small difference, right. But imagine that you go to a jeweler's shop and you're buying diamonds, okay, and now all of a sudden, right, even though in your exam paper you might not worry about a couple of decimal places here and there, right, here you want to be absolutely sure that the weighing scale is accurate to 6 decimal places, right, okay. So, there are a lot of applications where you have to it turns out that you have to measure a voltage where you need a very very accurate reference voltage. Now, the question, and when I say accurate, it basically must not vary with ambient temperature, right. I mean, so you do not want the weight to be different in an AC room, right, in the jeweler shop, and then you come home and then in Chennai it's 50 degrees and then you wait and then suddenly you find that oops, I've been conned, right. The gold only now weighs like 0.2 grams less, so I better go and fight, right. So, you want a reference voltage which is absolutely constant with temperature, right. Now, the question is, of course, it must be constant with temperature, it must also be constant with, it must not depend on supply voltage, right. So, and it should also ideally not depend on, variations of components inside whatever box you make. Your box is supposed to give you a constant voltage. Now, maybe that's 1 volt, 1 point, whatever, right. But you want to make sure that this does not depend on temperature and it does not depend on some extraneous factors like, right, like supply voltage, I don't know, I mean, how far your neighbor is from you and so on, right. So, it must be an absolute constant. So, the first thing to attack is basically the problem with temperature. I mean, can you think of, we have seen so many components, right, diodes, MOS transistors, PMOS, NMOS, etc., etc. Can you think of any voltage which will remain, which can act like a I mean, which seems reasonably constant. Pardon? Oh, okay, I mean, well, he says a Zener diode. I don't know how many of you have heard of a Zener diode. Have you heard of this before? Yes. Okay. Well, if you did, I mean, even easier than a Zener diode. Normal diode. And what about the normal diode? Yeah. So, well, in all our problems, we said the voltage across the voltage drop across a forward bias diode is 0.7 volts. So that seems like a reasonable place to start. So you take a diode and then bias it, push some current through it, right? And to first order, we said that the voltage is about 0.65 to 0.7 volts, right? In reality, it is VBE 1, which is basically VT ln I by IS. I mean, we should be, I think, particularly naive to assume that this will remain this points. I mean, this 0.65, 0.7 volts is merely an approximation. We'd be silly to believe that that's valid across all temperatures, especially when you look at the formula, right? That VT is of course KT by Q and is varying with temperature. More importantly, for those of you who have done a devices class, what is that IS? What happens with the saturation current as a function of temperature? Yeah, it basically is exponential, I believe, right? So, so IS increases with temperature, right? And therefore, and that's in the denominator. So, what comment can you make about VBE? For a given I, if IS increases exponentially with temperature, what comment can you make about VBE1? It decreases with temperature. So, actually if you go and measure it, it turns out that if you plot VBE, there is a reason why I am calling it VBE1, but with absolute temperature, it turns out that it's reasonably well approximated by a straight line with a slope of, does somebody know? No, we either know it or you don't. It's just information. It's not some big insight. Okay, so it just turns out that it has a negative temperature coefficient of 2 millivolts per Kelvin. Okay, but what we want is something which does not change with temperature. So, if you have something which is falling with temperature, how do you get a quantity which does not change with temperature? Common sense tells us that if you found some other quantity which increased with temperature, then if you add that and this in the right proportion, you will probably get something which does not change with temperature, right. So, this kind of characteristic which reduces with temperature is what is called CTAT, or short for complementary with absolute temperature. All right. Okay. Now the question is, so now, so we have a CTAT. To this we need to add something with positive slope. So that basically is what is called a PTAT, which is something which stands for proportional to absolute temperature. So, what temperature we need to add therefore to this VBE1 a voltage with a positive temperature coefficient of plus 2 millivolts per Kelvin. If you add that to this, the result will be something which is flat over temperature. Does it make sense? All right. So, now this characteristic we have. Now, the question is, how do we generate something with a positive temperature coefficient, correct? And some clever guy basically recognized that basically if you take the same current and put n diodes in parallel, okay. So, this is VBE1. So, what is VBEN? All the diodes are identical. I take this is just nothing but n such diodes in parallel. VT over n times Is. Correct? Alright. So, what is VBE1 minus VBEN? VT ln n. Okay. Does n change with temperature? No, it is just the number. Fortunately, Ln does not change with temperature, right. The only thing that changes with temperature is Pt, which is Kt by Q, where K is Boltzmann's constant, Q is charge on an electron, and so this is ln, correct. And therefore, what is the temperature coefficient of Vt of this delta VBE? K, which is basically nothing but Vt by T ln n times T, correct. So, the temperature coefficient is Vt ln n by T. Okay, this is just easier to calculate instead of doing K by Q, which I am sure most of you have forgotten what K is and what Q is, right. What is Boltzmann's constant? At 300 Kelvin, the temperature basically it is easy to calculate the temperature coefficient at some known temperature. We know that at 300 K, Vt is about 25 millivolts, 26 millivolts. I like to round things off. 25 millivolts by T is 300. So, this is ln n, okay, which is approximately ln n by 12, is it 12? Yeah, 12 millivolt per Kelvin. Or have I made a mistake? It's fine. All right. So, we need this to be equal to, we need this to be equal to 2 millivolts. So, we need, so if we, so VB1 is minus 2 millivolt per Kelvin. To this we must add some, this obviously ln n by 12, if this has to be plus 2 millivolts per Kelvin, then ln n has to be e raised to 12, right. That is, you have to cover all of Chennai with diodes, and then only then you will get the required this thing. So, the smarter thing to do is you generate whatever you can with a practical n and you multiply it with some gain k. Is this clear? Nothing, by the way, nothing prevents you from making that n very large, right, but that does not seem like a practical idea given real estate prices in Chennai. Okay, all right. So, k times Vt ln n, right, this must be chosen so that this has plus 2 millivolts per Kelvin, which basically means that k ln n by 12 must be equal to 2 left side is millivolts per Kelvin, right side millivolts per Kelvin. So, which basically means that this K ln n must be equal to 24, right. Okay. So, if K ln n equals 24, which is equivalent to saying that if you take a VBE of a transistor, I mean, so I am sorry, a diode, right, and most of the times it turns out that the diode is realized as a transistor with base and emitter, base and collector shorted. So, that is why I am calling it VBE, okay, but it is actually basically a diode drop. So, basically what is the moral of the story? It is telling you that if you take a diode voltage, to it you somehow add K ln n times Vt, and that K ln n must be, as per our math, 24. If you add 24 times Vt to it, the temperature coefficient of the result will be 0. Temperature coefficient will be 0. So, the voltage will be a constant, right. So, VB roughly 0.65, 650 millivolts roughly, right. 24 Vt is 24 and 25 is how much? 600 millivolts. So, 650 plus 600 is how much? It is about, about roughly about 1.25 volts. Okay. So, you will get a reference voltage which is 1.25 volts, constant with temperature. Alright, this is the principle. Alright, okay, and this is very similar to, the principle is not, I mean, it's as you can see, this is not rocket science, right. Long ago, I mean, when I don't know how many of you have actually seen a pendulum clock. How many of you have seen a pendulum clock? Okay, good, right. You know that the time period of oscillation of pendulum is what, 2 pi square root L by G, right, and in the good old days, they made that pendulum with some kind of metal, and of course, the metal will expand with in summer and contract in winter, and therefore, the pendulum will run faster in winter, and I mean the clock will run faster in winter and slower in summer, right. So, okay, which of course is no good. I mean, for most people it's okay, I suppose, but if you are on a ship and you thought you will get to island A after so many hours, then and you find that you are then you see only red Indians suddenly, then a big problem, right. So, thermal expansion is a problem, right, because of the positive temperature coefficient of the metal, right. So, once people figured that out, what would they do? You either make an alloy which combines metals with in the right proportion, so that the net temperature coefficient is 0, right. That alloy is called INVAR, okay, stands for invariant, right. And or otherwise what they would do is they make a hollow tube, right, of one metal. Inside they will pour mercury, right. So, what would happen? The hollow tube will expand downwards. Inside there is mercury. In the hot weather, the mercury column expands in the opposite direction, and with the right amount of mercury, you can basically make sure that the center of gravity of the pendulum remains positive, right. So, I mean basically as you can see, this ain't the principle isn't rocket science, correct. So, now well, the principle, there is one thing, the principle is one thing, but actually realizing it is something else, right. VBE1 is straightforward. You take some current, plop it into a diode, and you are all set, correct. But what we need to now do is, now how do I do this KVT ln n? The question is, how do I take some Vt ln n, right, which is the voltage difference between this, this simply is nothing but VBE1 minus VBE n, correct, and I need to multiply this by k, alright. There's so many ways in which you can think of doing this, which explains that why there are so many band gaps topologies around. We'll just do a couple of them just so that we get intuition as to how circuits are designed. Okay. I mean, of course, it's if you open the textbook, you'll have the final circuit and you analyze it, and sure enough, it'll all work, right? But it's always important to understand how the circuit came about in the first place. So remember, whenever we want to amplify a voltage, right? So for example, I don't know. I mean, your for example, say your familiar 1 plus R2 by R1 circuit. What is happening? This current is Vi by R1. That is basically converting the input voltage into a current, making that or pushing that current into a large resistor, and therefore getting a large output voltage, right? So the principle of amplification, I mean, same thing with the common source amplifier. What are you doing? You're applying voltage between the gate and the source, generating a current which is Gm times the input voltage, passing it through a large resistor in the drain, right? So the basic principle of amplification is always you convert voltage into current, take that current, push it into a large resistor, and therefore get a large voltage at the output, right? So if you want to therefore amplify this Vt ln n, which is basically Vbe1 minus Vben times n times k, the first step is to convert Vbe1 minus Vben into a current and push that current into a large resistor so that you get a large multiple of Vbe1 minus Vbe. Is this clear? All right. So I mean, let's do things simple things first. Rather than try to amplify Vbe1 minus Vben, the first step, let's try and figure out how to convert Vbe1. Let's try and amplify Vbe1 first, right? And from that intuition, hopefully we will be able to figure out Vbe1 minus Vbn. So if you want to convert this Vb, we have some Vbe1, we want to convert it into a current. What do you think we can do? Let's say if we want to convert it into a current, say Vbe1 by R, right? And if you're in a lab and you have a variable current source and you want that variable current source to be equal to Vbe1 by R, what do you think you will do? Very good. So you have some variable current source, you will pass it through so you will put so this is I, this voltage therefore is going to be IR. So you will put a voltmeter and go and turn the knob on I such that Vbe1 equals IR, right? But now you are all experts at this. So now so if IR is less than Vbe1, what does it mean? I is very low, you must increase I, and vice versa, correct? Okay. So in other words, you need a you basically need to control that current. I is controlled by the difference between Vbe1 and IR, that 2 volt voltage. Okay. So now, I mean, of course, you can't keep sending a technician every time you want to convert a voltage into a current. Whatever you can do, the moment you describe it clearly, you can get an electronic circuit to do it, correct? So this current source, this current is pushing down and it's variable. So can you think of some component that you already, some device that you already are aware of, which can push current and you have control over that current? You need a current to be pushed down. PMOS. All right. All right. Okay. Now this is the knob, and you must compare VBE1 with that node IR and go and kick the gate of the transistor in the right direction. So, all right. So, if VBE1 is if IR is less than VBE1, we must increase I, which means that VG must, we are basically looking at VBE1 IR controlling VG. So, if VBE1 is less than IR, if IR is less than VBE1, it means that the current is too small, which means that VG is too high, and I must therefore reduce VG. So, VG must reduce, okay, and vice versa. Okay. All right. So, this is a voltage controlled voltage source. So, VG is a voltage, must be controlled by the difference between these two, and what must be the gain of that voltage controlled voltage source? Even if I see an infinitesimally small difference between VBE1 and IR, I must go and kick the gate so hard that the difference becomes 0. So, what should be the gain of that voltage controlled voltage source? Infinite, right. So, what is that animal which has an infinite voltage what is the voltage controlled voltage source with infinite gain? Opamp. All right. All right, and what are the signs on the op-amp? If IR is less than VBE1, the gate must be pulled down. So, IR positive or negative? Positive. Is this clear? If you're not convinced, if I break the loop here and yank this voltage up, what comment can you make about that node voltage? Goes up. If that goes up, what comment can you make about that voltage? Goes down. So, there is negative feedback. So, basically, therefore, what happens to I therefore? VB1 by R. All right. But what we want is not VB1 by R, we want VB1 minus VBN by R. Okay. So, any suggestions? Why is this current VB1, this voltage therefore is because the op amp has infinite gain. What is the voltage on the right hand side? VBE1, correct. So, this current is VBE1 by R. If I want VBE1 minus VBN by R, what do I do? Okay. So, if you had a battery of value VBN, right, you will get the current that will flow is VBE1 minus VBN by R. Okay. And so, VBN is nothing but N diodes in parallel. Okay. So, this will give us VBE1 minus VBN by R. Okay. So, we will continue in the next class.